In today's video, we're going to be taking a look at the high-speed CAN communication network, and we're going to be using the Picoscope for this, and we're also going to be looking at how to use this serial decoding that is built into the software. So to help us with this, we have our breakout box plugged into our OBD2 port, and high-speed CAN communicates on pins 6 and 14, and this breakout box labels everything for you right here. So you can see I have channel A plugged into the CAN high, pin 6, and channel B plugged into pin 14, which is the CAN low, and then I've piggybacked our grounds into the chassis ground location right here. Now, every vehicle sold in the United States since 2008 has been required to have high-speed CAN communication on pins 6 and 14, and some of the vehicles before 2008 you might have high-speed CAN as well. This one we're working on today is a 2007 Toyota Camry, and it has it. Okay, so let's get started setting up the Picoscope for this. This is a 2-wire communication network. The wires will sit recessive at 2.5 volts. The CAN high wire will get pulled up to 3.5 volts, and the CAN low will get pulled down to 1.5 volts. So we're in like a plus or minus 5 volt range, but you tend to get a little bit of noise, so I usually keep it at plus or minus 10 volts on channel A and channel B. And then as far as the time goes, we want to increase our sampling rate to the highest it can be. But just keep in mind that when you turn that sampling rate up, the time affects the sampling rate. So even though I turn it all the way up, does not mean I'm going to get 10 gigasamples per second like it says right here. So we go back to the time base. Right now it's defaulted to 20 milliseconds per division, and notice the sample rate is 200 megasamples per second, which is really good. If I go to 50 milliseconds per division, it already drops down to 100 megasamples per second, and the higher I go with my time base, the more sampling rate I'm going to lose. If I drop down to the 10 milliseconds, I can maintain that 200 megasamples per second. So I really just want to pick the highest time that I can record while still maintaining the highest sampling rate, and so that happens right here at the 20 milliseconds per division. Okay, now that we got the Picoscope set up, I've started the car. We are now running, and you can see that the signals are active. We're going to pause that just for a second. We're going to zoom in on one of these packets of information so you can see what they look like. And as I said before, it sits recessive at 2.5 volts, dominant on the high side at 3.5, and on the low side at 1.5, and it should look like a pretty good mirrored image like we see here. Now that we've captured our data, let's go ahead and analyze what we have. So we're going to zoom back in like we were before. And looking at how those signals are mirrored is really the way you analyze whether or not you have communication errors and things like that. I've made a few other videos if you want to go watch them on how you can tell when the high or the low is shorted out, or if there's an open. So you can usually catch those big problems just by turning on the scope and watching the live communication between the modules. However, there are times when like a module is causing a weird signal and there's lack of communication codes and things like that that are a little bit more intermittent. And so to find those intermittent issues, sometimes watching it live like this isn't always the best way to go. So that's why we're going to use this serial decoding over here. So let me show you how to set that up. So when you're going to decode one of these CAN bus messages, it's important to think about what the PCM is actually looking at. It has 2 lines for a reason. There's a reason that these are mirrored images, and it's because the computer is always going to be looking at the differential between the two. So when I decode, like when I click on this box, it's going to give me the option to either decode the high or the low, which works, but what I like to do is something similar to what the PCM is doing. I like to look at the differential voltage and decode it from there. So to do that, I'm going to put up a math channel, and we're going to take channel A minus channel B right here. And now we have that differential pulled up. So the difference between when they're both at recessive is 0, and the difference between them when they're both at the dominant is 2 volts. So 0 to 2 volts scale right there. Now that we have that set up, we can go ahead and click on the serial decoding, click on CAN up here at the top, select the A minus B channel that we've turned on, and then for our threshold voltage, since we're going between 0 and 2 volts, we're going to put it right in the middle at 1 volt. The next thing that we do is this hysteresis. Basically what this is, knowing that there's bound to be some imperfections on the CAN bus, considering the length of the wires and the speed of their communication, the program builds in this hysteresis, which is basically going to ignore some of the anomalies that you might see. So the higher you turn this number up, the less sensitive this becomes to errors. So I like to turn it to 0 volts and make it more sensitive so we can see if we pick up one of those intermittent problems that we're looking for. High-speed CAN communicates at 500 kilobauds. We'll turn that to that, and then we'll just leave that at high. And then we're going to, for this video, look at the binary, and now we just click finish. Once we click finish, we get this new box down here at the bottom of our screen, and there's also a ribbon that shows up here on our screen, which we'll look at in just a second. So let's look at this box a little bit closer. And inside you can see each packet of information and the binary code that was sent. If you click on one of these, or double click, it takes you to that exact message up here. And there's that ribbon that I was telling you about that we'll look at a little closer here in a minute. Now, I said before that serial decoding was helpful in finding intermittent issues in your CAN communication. So notice how everything down here is colored in black, and we have all these check marks over here. That means that all of these messages were considered valid and there was no errors seen. If you see it colored in red on here and you see an X in this box over here, then you know that it had a failed message. So if you click on this box, you can reorder this and find out if there's any red checks or red X's in here. And this actually has none, which is really good. And that's what we're hoping for. If you see those red ones, then obviously go to them, double click, take you to the message, and you can figure out what went wrong up here. The last thing I want to look at with you is what this ribbon actually represents and what all of these little columns down here represent. So let's go ahead and zoom in on this one message that we have. And you can see when we do that, that the binary code actually pops up within the ribbon. And then obviously you can see there are different color-coded sections so that we know the different parts of the message. And that's what each of these columns represents down here as well. So this yellow section right here is the identifier for the message. So basically this portion sets the priority of the message. So if there's multiple messages sent out on the bus at the same time, whichever one has higher priority will take precedence. And you can know which one has the higher priority by the numbers of zeros that you see in here. The more zeros you have, the more the priority. This green section we don't tend to use very much when we're looking at this. The blue-purple is the actual data that was sent in the message, and there can be 8 bytes in here, and this message that we're looking at does have 1, 2, 3, 4, 5, 6, 7, 8, and each byte has 8 bits in it. Okay, down here in the blue, this is your redundancy check, and this is basically the computers making sure that there aren't errors in the message. So it looks at what the computer sent and it verifies that the other computer got the same message. The last thing here is this acknowledgement bit, and I like this the most because if it acknowledged the message, then the message was probably valid. So this looks like a great message right here. One more thing that I wanted to show you is these little gray spots up here at the top of the ribbon. These are called bit stuffing. So when you have a bunch of zeros being sent in the message in a straight line like this, the computer starts to worry that maybe it's shorted out or something like that. And so it throws in a 1 just to prove that it can, right? Just to prove that the message isn't stuck at 0 the whole time. So after about 5 zeros, it'll throw in a 1, and then we can continue on, and then it will throw in a 1 again if we need to, and that is what bit stuffing is. So since the data that we recorded off of the Toyota Camry didn't have any errors, I wanted to pull up another vehicle. This is a Ford Fiesta, and it has a few errors down here. So I've double clicked on this one, and you can see, I still have the ribbon and everything, but the ribbon doesn't extend to the end of the message. And if I hover over the top of it, you can see that it says that it was not a valid message. You'd even failed the redundancy check on this one. So that's what it looks like when you're looking for errors. So this, like I said before, could be really helpful if you're trying to find intermittent issues with your CAN communication. Hopefully that helps you guys out there. I'm going to make another video on one other way that you can use to help find intermittent problems. So keep an eye out for that.